Okay, so in this section, we're going to be talking about conditional probability and the multiplication rule. So I want to start off with a definition. So the definition of a conditional probability is simply that it's the probability of an event happening given that something else has already happened. So you have a condition, something has happened that's affecting whether something else is happening. Okay, so we're going to go ahead and, well, I guess first we need to talk about the notation. So we notate this by P of A with a vertical bar A, and we read this as the probability of the event B given event A has already happened. Okay, so let's go ahead and take a look at this first example. It says we have two cards that are selected in sequence. In other words, two cards that we draw one after another from a standard deck of 52 playing cards. Okay, so I'm going to stop here really quickly, and at the very end of these notes, I did give you a list of all the cards that are in a 52 card deck. Okay, so if you are confused on what that contains, go ahead and refer back to that anytime you see a 52 card deck. Okay, so it says find the probability that the second card is a queen given that the first card is a king. Okay, so what we're saying here is we're looking for the probability of drawing a queen given that we've already drawn a king. Okay, so if you draw a king, know that that is, we have four cards. If the probability of drawing a king is 4 out of, well, there's 52 total possible cards, right? So it's the number of favorable outcomes divided by the number of possibilities. Okay, however, if we draw a king out of this, right, so we've drawn a king out of our deck, that means we no longer have 52 cards. We actually only have 51 cards left. Okay, however, how many of those are queens? Well, we have 4 queens, right? And so we can simplify this, and we can say, well, this is equal to 0.078, or if you were to change this to a percent, it would be 7.8%. Okay, and so that's all we're looking for here. Again, the top refers to the number of queens, and the bottom refers to the number of cards in the deck. Okay. All right, so let's go ahead and take a look at Part B. So Part B says the table shows that the results of the survey in which 2,276 social media users were asked whether they have ever been offended by something they saw on social media. We want to find the probability that the user is male given that they were offended by something on the social media. Okay, so what we're looking for here is the probability that they're male given that they've been offended. So I'm going to just leave O. I'm going to say that O represents the offended. Okay. So if we were to set this up, okay, the bottom number is going to be the total number of people who are offended. Okay, so we're given that that someone is offended. So we're looking at the total number of people who are offended. Okay, and then the top is going to be the number of males that were offended. Okay, so the number of males offended. All right, so if we were to write these, notice that we're looking, it's the total out of the number of offended. So we're looking at this column here. Okay, so the ones who said, yes, I've been offended at some point. Okay, and the way we'd set this up, well, we have a total of 1,151 people who were offended, and of those, 619 were male. Okay, and we could obviously change this to a decimal. So changing this to a decimal would give us 0.462. So the probability that if they're offended, they're male, well, it's about 46%. Okay, so there's a 46% chance that they'll be offended. All right, so let's kind of change this up. So I'm going to go ahead and do one more example. Okay, just to kind of to run this home. So this time, let's go ahead and take a look at what's the probability that someone is offended given that they're female. Okay, so what's the probability that someone gets offended given that they're a female? Well, notice that the given part is the bottom. So we're given that it's female. So we're looking at this row here. Okay, so total we have 1,168 females. Okay, now how many of those females were offended? Well, there are 619 females who were offended. Okay, so using your calculator here, you can simply divide them out. So 619 divided by 1,168 gives you about 0.530, or about 53% of those who were women were offended. Okay, all right. So now to move on, we're going to talk about the difference between independent and dependent. Okay, so two events are independent when the occurrence of one event does not affect at all the probability of the second event happening. Okay, and the way we can simplify or to show this would be we have the probability of B, given that A has already happened, is actually equal to the probability of A. And same thing with the reverse. So the probability of A, given that B has already happened, because they're independent, means that the probability that's equal to the probability of A. Okay, so as long as they're independent, we can say that the probability of B given A is equal to the probability of B, and the probability of A given B is equal to the probability of A. And we're going to use this here in a little bit when we talk about some of the other definitions. Okay, and so events that are not independent are considered to be dependent. So in other words, the outcome does in fact affect, so the outcome of one does affect the outcome of the other. So if I were to draw a card out of a deck and not put it back, that would be considered a dependent event, where if I were to draw a card out of a deck and I put it back into the deck, because we didn't change the number of total cards in the deck, it doesn't affect it. Okay, so that would be independent. So let's go ahead and look at example 2. It says we want to determine the events, whether the events are independent or dependent. Okay, so smoking a pack of cigarettes per day, that's event A, and developing emphysema, and that's event B. Okay, is this independent or is this dependent? Does the probability, or does the fact that we smoke a pack of cigarettes per day, does that affect whether or not we develop emphysema? Well, yeah, it does. Okay, so these would be dependent. Okay. Now looking at part B, it says tossing a coin and getting a heads, that's event A, and then tossing a coin and getting a tails, that's event B. Now, if we flipped a coin, does getting a heads on the first flip affect whether we get a heads on a tails on the second flip? Well, no. In this case, these would be independent. Okay, so we've got dependent and independent. And this is going to be important because if something is independent, then we can simplify our equation. So let's go ahead and talk about the multiplication rule really quick. So the multiplication rule is if we have two events, A and B, the probability that they will happen in sequence is the probability of A times the probability of B given A if they're dependent of each other. Okay, if they're independent, we can simplify that to this. Okay, so this is the first one is basically saying that we're looking at the probability of A and B happening if we're taking stuff out and not replacing it. So if it's affecting something. So the probability of A and B is this. We would use this one if we have something affecting the outcome of the other one. Okay, where the second one is if it's entirely independent. So we can use this one if it's dependent, and we can use this one if it's independent. Okay, in fact, on the top one, we can actually use it if it's either one. And the reason being is that if it's independent, remember that the probability of B given that A has already happened is shown up here. So the probability of B given A is simply the probability of B if it's independent. Okay, so that comes from the definition of independence. Okay, so we can use the top one for either one, but if we know that they're independent, we can simply use the second one. Okay, So let's go ahead and do an example of this. So we have two cards that are selected without replacing the first card. So this is an important statement here. So without replacing the first card. Okay, that means we're taking cards out and we're not putting them back. From a standard deck of 52 playing cards, we want to find the probability of selecting a king and then selecting a queen. Okay, so we're looking here. So we're looking here for the probability of a king and a queen. Okay, so the probability of selecting a king, well, we have 4 kings out of a 52 card deck. Okay, now because we're looking at a king and a queen, so that's the probability of A, right? Now we need to find the probability of B, given that A has already happened. Okay, so this time we're looking at the probability of having a queen. Well, we have 4 queens in the deck. Now, how many cards total do we have a deck? Well, remember that we're not replacing these cards. So instead of 52 cards, we actually only have 51 cards. Okay, and so when we simplify this, we get 4 out of 663, which is equivalent or approximately 0.006, or about 0.6% chance that we'll draw a queen and then, a king and then a queen. Okay, so let's go ahead and take a look at this next one. So that was without replacing, so they were dependent on each other. Let's take a look at part B. It says a coin is tossed and a die is rolled. Now, are these independent or are they dependent? Well, tossing a coin does not affect the probability of something happening on the die. So tossing a coin and rolling a die, those are independent events. Okay, so if I were to look at this is the probability, well, we're looking at a heads, so probability of rolling a heads and rolling a 6. Okay, so these are completely independent. They don't affect the outcome of the other. Okay, so the probability of tossing a heads, well, that's 1 in 2, right? So there's 1 heads on a 2-sided coin times, well, the probability of rolling a 6, well, there's 1 out of 6. Okay, so we multiply across, we get 1 out of 12, which is approximately 0.083. Okay, so about 8.3% chance, or a little bit less than 10%, that we can flip a heads and then roll a 6 on the die. Okay, so example 4. Again, we're continuing with the multiplication rule. It says for anterior cruciate ligament, the ACL, reconstructive surgery, the probability that the surgery is successful is 0.95 or 95% chance that it's successful. What is the probability that all 3 are successful? Okay, so we're looking for the probability that we have a success, then a success, and then another success. So 3 successes in a row. Okay, so the probability of the first success is 0.95. Now, one thing we need to take a look at is this dependent or is this independent? Okay, so does the success of one surgery affect the success of the second surgery? Well, in this case, no. Okay, so the success of one does not affect the success of a second one. Okay, so these are independent. Okay, so the probability does not change. So the probability of the first one is 0.95. The probability of success on the second ACL surgery is 0.95, and the probability of success on the third one is also 0.95. Okay, using your calculator, we can simply multiply it out. We get about 0.857. And you'll notice that on all of these, I like to round to the third decimal place, and that just kind of gives you, if you ever do convert it to a percentage, it gives you a decimal place when converting it to a decimal into a percent. Okay, so that's why I'm rounding everything to the third decimal place. So if it does not say to round, just round to the third decimal place. That's typically okay. Okay, so now what's the probability that none of the 3 ACL surgeries are successful? Well, I'm going to find the probability, and I'm going to label this by maybe just use. So unsuccessful, unsuccessful, and then an unsuccessful. Okay, so 3 unsuccessful surgeries in a row. Well, the probability of having a successful surgery is 0.95. Okay, so that means that the probability of an unsuccessful is the complement of that, so 0.05. Okay, so remember, we learned about complements in the last chapter, or in the last section. Okay, and again, these are independent events. So if I were to find the probability, I simply have to multiply the 3 times we had a surgery and the 3 failures we had together. Okay, so 0.05 times 0.05 times 0.005, and we get just about 0.0001. That's our probability. Okay, and if we were again to change this to into a percentage, it's actually a really small percent chance that we have 3 unsuccessful surgeries in a row. Okay, so that person has to be extremely unlucky in order to get to have 3 failures in a row. Okay, so the third part, it says find the probability that at least one of the 3 ACL surgeries are successful. Well, the probability of them being successful, well, we could have the first one being successful, the second one being successful, the third one being successful, right? That's one set of probabilities. We could say the first one's successful, the second one's unsuccessful, the third one's successful, right? And then we could say, well, the first one could be successful, the second one could be unsuccessful, the third one could be unsuccessful, and we could keep going on forever and ever and ever, and we'd have to do a lot of work here in order to find it out. Now, another way to do this is that we can find the complement, right? So at least one means that what we could do is instead, because we're looking at least one, so from 1 to 3, we could instead just find the probability that none are successful. Okay, so find the probability that none are successful. Notice that we have already done that up here. And then subtract it from 100%. Okay, so the probability that at least one is successful, so the probability that at least one is successful. Okay, so I'll go ahead and change that. So we'll just say at least one is equal to, well, we know the probability that none of them are successful, so if we subtract that from 100, that'll be at least one being successful, okay? And we get about, or 0.9999, so nearly 100% chance that at least one of those will be successful. Okay, so moving on. In a jury selection pool, 65% of people are female. Of these 65%, 1 out of 4 works in a healthcare field. We want to find the probability that a randomly selected person from a jury pool is female and works in the health field. And then we're going to determine whether this is unusual. So again, we're going back to the definition of unusual in the very beginning. So unusual, remember, is less than 5%. Okay, so taking a look at this, so we're looking at the probability that they are female and they work in the health field. Okay, so the probability that they're female, well, that's 65% or 0.65. Okay, the probability that they work in the health field, well, that's 1 out of 4, which is 25% or 0.25. So we can simply multiply those, right? And we multiply these out, and we get about 0.163, and that equates to 16.3%. Now, is this unusual? No, it's not unusual. Okay, again, because it doesn't fall below that 5%. Okay, in this next example, we're going to say, well, what's the probability that we randomly select a person from the jury pool that is female and does not work in the health field? And is this unusual? Okay, so to determine this, well, we know that the probability that they're female is 65%, and the probability that they, not health, and the probability that they do not work in the health field is, well, it's the complement of 25%, so it'd be 75%. So again, it's 0.65 times 0.75, right? So this is the probability that they don't work in the health field in this jury selection. Okay, so we multiply those together and we get about 0.488. And again, because this is not less than 5%, it is not unusual. All right, and then lastly, I have this deck of cards summary. So if you are not familiar with the deck of cards, this is here for you guys